Hey everyone, and welcome to this explainer. Okay, so when you hear the word chemistry, what pops into your head? You're probably picturing glowing liquids, crazy complex glassware, and someone standing there in a really crisp white lab coat, right? Well, let's just shatter that stereotype right now. The truth is, chemistry absolutely did not start in a sterile laboratory. It actually kicked off with our Stone Age ancestors chipping away at pieces of flint to make useful tools and carving wood. That right there was the very beginning of humans manipulating matter. Think about this quote for a second. Humans began to practice chemistry when they learned to control fire. It kind of blows your mind, right? Manipulating matter is fundamentally this ancient survival skill. When early humans figured out how to use fire to cook their food, bake bread, or smelt copper ores into tools and weapons, they were literally practicing chemistry. They were actively changing the composition of substances just to survive and thrive. And that sets the stage perfectly for what chemistry truly is at its core. It's the study of the composition, properties, and interactions of matter. Okay, let's dive into this. Here is the roadmap for our explainer today. We'll start with 1, from alchemy to modern chemistry, then move to 2, the central science, break down 3, the scientific method, and finally unlock the perspective of chemists in 4, macro, micro, and symbolic. So, section 1, from alchemy to modern chemistry. Let's look at this historical journey. Just look at the sheer scale of this timeline. We start way back in the Stone Age, simply shaping flint. Then we move to antiquity, where humans are harnessing fire to extract dyes like indigo and Tyrian purple, and mixing copper and tin to make bronze. Fast forward a bit to the 1580s, and you have the alchemists spreading all across Egypt, China, and the Eastern Mediterranean. Now, they were trying to transform base metals like lead into gold, and brewing up these wild elixirs to cure diseases. And sure, while alchemy wasn't scientific by our modern standards, it laid the essential groundwork for how we manipulate matter. And that directly paved the way to the 1930s and 40s, the era of modern methodical drug synthesis. I mean, that is a massive leap, going from mystical elixirs to precise, targeted medicine. To see how this actually plays out in the real world, look no further than the absolutely groundbreaking work of chemist Percy Lavon Julian. So back in the 1930s and 40s, certain life-saving medicines were incredibly scarce. Progesterone, for instance, had to come from animal sources in these tiny, massively expensive quantities. Cortisone required a grueling 36-step process just to synthesize. Well, Percy Julian did something brilliant. He turned to soybeans. They were plentiful, they were cheap. By focusing on soy sterols, which are these substances found right in the plant's membranes, he figured out how to synthesize progesterone, testosterone, and eventually cortisone in massive quantities. He essentially laid the groundwork for modern drug design, taking an abundant plant and turning it into medicines that saved and improved countless lives. All right, moving on to section 2, the central science. Here's how chemistry really connects everything in STEM. Chemistry is basically the grand junction for almost every scientific field you can think of. Biology and medicine, they rely on it entirely to understand the complex biochemical processes that keep us alive and to design the pharmaceuticals that keep us healthy. Physics shares a massive overlap with chemistry in areas like chemical physics and nuclear chemistry. Environmental science and geology use chemical ideas to understand our physical world, everything from oceanography to atmospheric science. Materials science and nanotechnology are combining chemical principles right now to produce everything from new fabrics to super advanced electronics. Agriculture and food science use it to provide sustenance to the entire global population. It even extends all the way out to astronomy and cosmology, where chemical ideas are used to understand the vastness of the universe itself. Chemistry is literally the vocabulary connecting all these disciplines. Up next, section 3, the scientific method. Let's talk about observation and experiment. So, unlike the philosophical guesses of the ancient Greeks who, thought everything was just earth, air, fire, and water, and unlike the mystical attempts of the alchemists, modern science is firmly based on observation and experimentation. Now, there's no single perfectly neat route to a discovery, but the process does follow a general iterative loop. Step 1 usually starts with an observation and a question. Step 2 is forming a hypothesis. Step 3 is experimentation, and step 4 is theory formulation. The core of this entire process, the thing that makes it work, is that it relies absolutely on reproducible experiments. You have to be able to verify your results. Open inquiry and constantly reworking your ideas in response to new findings, that's what guides true discovery. So, the crucial point here is understanding exactly what a hypothesis is. A hypothesis is a tentative explanation of observations that acts as a guide for gathering and checking information. It's definitely not a wild guess. It is a starting point that must always be tested. You test it by experimentation, by calculation, or by comparing it with the experiments of others. And then you refine it as needed. Now, contrast that with a scientific law. A law summarizes a vast number of experimental observations, describing or predicting some facet of the natural world. It doesn't necessarily explain exactly why something happens. Rather, it's a really solid summary of behavior that has been observed countless times. If a hypothesis turns out to be capable of explaining a huge body of this experimental data, it can kind of graduate, so to speak. And that graduation leads us to a theory. A scientific theory is a well-substantiated, comprehensive, testable explanation of particular aspects of nature. We accept theories because they provide highly satisfactory explanations of the world around us, but, and this is honestly a beautiful part of the scientific method, they can always be modified if new data emerges. The scientific method isn't rigid, it's a living, breathing process. Which brings us to our final part, Section 4, macro, micro, and symbolic. These are the unique domains of chemistry. This is where we give you the foundational decoder ring for the whole field. Ask yourself, how do chemists actually see the world? When a chemist looks at a glass of water or a burning fire, what is happening in their minds? Well, it turns out chemists describe the behavior of matter in 3 very specific, distinct domains. Waking up to this conceptual shift is really what makes chemistry so fascinating. Water is honestly the perfect way to brilliantly illustrate these 3 domains, using something we all interact with every single day. First, we have the macroscopic domain. This is what we sense with our human sight or touch, like giant icebergs, the ocean, or the humidity you feel in the air. Then we have the microscopic domain, which must be visualized in the imagination or with highly advanced tools. This is the unseen realm of H2O molecules organizing into solid ice or disorganizing into gas. Finally, we have the symbolic domain. This is the specialized language used to represent these components, like writing H2O with an S for solid, L for liquid, or G for gas. Let's break these down just a bit more. The macroscopic domain is basically the realm of everyday things. Macro is a Greek word meaning large. So this is the world that is large enough to be sensed directly by human sight or touch. It's the physical breeze you feel on your face. It's the literal process of your body digesting food. It's measuring the physical properties of a substance in a lab, like checking its density or testing its flammability. In short, it's the chemistry you can actually hold in your hand. Now, let's zoom way in to the microscopic domain. Micro means small. Sure, some of this can be seen with standard microscopes, like biological cells, but the vast majority of subjects in chemistry's microscopic domain are far too small to be seen even with the most advanced optical microscopes. We're talking about ions, electrons, protons, neutrons, and chemical bonds. Because these are just too small to see, mastering chemistry requires a vast amount of imagination. You have to be able to picture these tiny interactions occurring right there in your mind. And finally, to connect the seen and the unseen, we use the symbolic domain. This is the specialized language, the chemical symbols on the periodic table, the formulas, equations, graphs, and drawings. Writing H2O with a little g for gaseous water is a perfect example of this. It translates this crazy microscopic reality of disorganized, rapidly moving molecules into a simple symbol we can write down, share with others, and calculate on a piece of paper. The biggest challenge, and honestly the greatest thrill, in learning chemistry is realizing that a single symbol represents behavior across both the macroscopic world you can directly observe and the microscopic world you have to imagine. As we wrap up this explainer, I really want to leave you with this one thought. Next time you feel the breeze on your face, or you watch bread rise and bake in the oven, can you picture the unseen microscopic interactions that are driving those macro changes all around you? Chemistry isn't just something happening in a textbook or locked away in a lab. It happens every single time matter changes form. Keep that decoder ring handy, and I promise you'll start seeing the central science everywhere you look. Thanks for learning with me today.